In this last example on how to solve a system of three equations with three unknowns, we're going to look at another special situation that could occur when you're in the solving process. To start off, I'm going to call the first equation E1, second equation E2, and the third equation E3. Remember, step one is to try to reduce this three equations with three unknowns into a system of two equations with two unknowns. I can pick any variable to eliminate that I please, and I notice that just by adding E1 and E2, I can cancel out the Z's. And if I add E2 and E3, I can cancel out the Z's. So with not having to do anything really, or any multiplication, I can just eliminate the Z's. So in this example, to save myself some work, I would choose to eliminate the Z variable by doing E1 plus E2, and then I would also use the combination of the second equation E2 added to E3. Both of those would result in dropping out the variable Z. If I go ahead and I solve or set up E1 plus E2, that will be X plus Y plus Z equals 2 for E1. The second equation, E2, is X plus Y minus Z equals 2. If we go ahead and add these, I'm going to end up with 2x's plus 2y's, and the z's drop like we planned, and that's equal to 4. I'm going to call that my new equation 1. If I solve these guys, E2 plus E3, that's x plus y minus z equals 2, and then I have 2x plus 2y plus z equals 4. If I combine those, I get 3x's plus 3y's, the z's cancel, and I get 6. I'm going to call that new equation 2. If I set up my second step, the two equations with two unknowns I now have are 2x plus 2y equals 4. That was new equation 1. And my second equation is 3x plus 3y equals 6. That was new equation 2. Now my goal is to eliminate another variable, kind of like we did in section 3.2. I'm going to show you guys a trick that I might not have had the opportunity to show you in class. Do you see how in this first equation I can divide every term in the entire equation by a 2, because 2 is a factor of each term? That will allow me to simplify this equation, and then makes my life a lot easier. So if I divide everything by 2 in this whole equation, this would become x plus y equals 2. I can use that instead. It's a lot easier to work with. Similarly, I can divide all of these terms in the second equation by the common factor of 3. That will reduce the numbers in the equation and make computations a lot easier. So I'm going to end up with x plus y equals 2. Right there, you'll notice these are identical equations. You should hopefully be thinking, this is infinitely many solutions. If you're not thinking that yet, let me continue and I'll show you where you'll recognize very clearly this special case. Let's just say we didn't notice that they were the same, and we chose to eliminate x by doing, let's call this still new equation 1 and new equation 2. I would eliminate x by doing, let's say, negative 1 times the top equation and just adding that to the bottom equation. If I do that, I'd get negative x minus y equals negative 2 for the top equation, right? The bottom equation, if I just add it, I'd get x plus y equals 2. When you add these up, x's cancel, y's cancel, and I get 0 equals 0. I hit a true dead end. That means there are infinitely many solutions. This is a case where if we were to graph all three of these planes in the same three-dimensional coordinate space, we would have either all the same plane, all three of them exactly the same plane, so there's infinitely many solutions on the plane, or they all intersect along one line where there's infinitely many solutions.